minimum of these particular functions going to be. So we call these absolute extrema. Again, when we talk about absolute extrema, we're talking about points where you have the smallest or the largest y values. So we use that blanket phrase absolute extrema to include absolute max and absolute min. Just like we have relative extrema, we use that phrase absolute. So when we talk about a function, and we could be looking at an interval that's all real numbers, we could be looking at a definite, finite interval to find absolute extrema. And if we're looking at this interval and we're looking at a point, let's say x sub 0, we can say f has an absolute maximum if at that particular x value all your other y values are less than or equal to the y value that's at that particular point x sub 0. So we can call that an absolute maximum. So you're doing a comparison of y values all along the function. So whatever point has the largest y value, that's going to be your absolute maximum. We also can say that f has an absolute minimum at x sub 0 if that particular y value is less than or equal to all the other y values in that interval that you're looking at. All right? Not all graphs may have an absolute max or an absolute min. It may have one or the other. It may have neither, that we'll take a look at in a few minutes. So we can say that f has an absolute extrema at x sub 0 if it has either an absolute maximum or absolute minimum. So again, that's the Bryant phase. Extrema is, again, you're talking about whether it's an absolute max or min. So first of all, let's take a look at some examples of what could happen when you're looking at graphs that have no domain restrictions. So you're looking at the interval for all real numbers. If you think about your quadratic functions or any even degree polynomial function where the leading coefficient is positive, you know that both ends, as the limit as x goes to positive or negative infinity, is going to infinity. So in that particular case, there is going to be no absolute maximum. But notice you will have an absolute minimum. So it's possible that you have a graph where you have an absolute minimum but no absolute maximum. And a perfect example of that is when you're dealing with a polynomial function of even degree, where the leading coefficient is positive. It is possible that you have absolutely no relative extrema over that interval from all real numbers. For example, take a look at all your linear functions. We know that the end behavior, as the limit goes to positive and negative infinity, is going to negative infinity on one side, positive infinity on the other. So therefore, there is no absolute maximum and absolute minimum. Again, you're looking at open intervals going for all real numbers. You may also have a case where you have both the absolute minimum and absolute maximums. So like I said, graphs may not necessarily have both. They may have neither. So now, if you take a look at graphs that have domain restrictions, it's possible you have to pay attention to whether or not the endpoints are included or not included when you're taking a look at these domain restrictions, because that's going to open up where my candidates are going to be for where my absolute maxes and mins could occur. So again, if you're not including the endpoints are not included in the domain, then you have to look for absolute extrema just between the endpoints. So in this particular case, for example, if this looks like a reflected negative x to the third, it also looks like it could be a possible reflected tangent curve. Notice there is no absolute extrema when you're going from the interval a to b, where a and b are not included. However, notice if I take this line and now I'm including my endpoints, your endpoints are now going to be candidates for where absolute extrema can occur. If you have a closed interval, then you will definitely have an absolute max and an absolute min. It may occur at the endpoints. All right? So that leads us to a theorem that's called the extreme value theorem. So your extreme value theorem states, first of all, the conditions have to be your function is continuous and it's a finite closed interval, meaning that you're including your endpoints, then as long as you have that finite closed interval, then your function will have both an absolute maximum and an absolute minimum on that particular closed interval. If you have a function in an open interval where you're not including the endpoints, then it must occur at a critical point. So if you have that open interval where you're not including the endpoints, then your absolute extremum has to occur at a critical point. And you guys know how to find those critical points. You find the first derivative, you set the derivative equal to 0. All right? So here's how we're going to find the absolute extrema of a continuous function for a finite. So finite means it has a definite start and definite end. Just like you find relative maxes and relative mins, you're first going to have to find the critical points in that particular interval again. So you simply take your first derivative and you're going to set it equal to 0. Now this part's a little different, because up till now when we've been finding the critical points, we've been concerning ourselves with increasing, decreasing, and concavity. Now we're concerning ourselves with what is the highest or lowest point on these particular curves. So now we're concerning ourselves with what are the y values on your actual f of x. So what you're going to do is you're going to evaluate f at all the critical points and at your endpoints. So your candidates of where your absolute extremum can occur is not only at the critical points when you have that closed interval, but also at the endpoints. So what you're going to have to do is you have to plug the values back into f of x, the original function. So what you're going to do is you're going to find the y values. So you're going to plug these values back into your original function, not the first derivative, not the second derivative. And when we have plugged these numbers in, you'll compare. And the largest value is the absolute maximum. And the smallest value you come up with is the absolute minimum. So really what's different than finding relative mins and relative max is you're going to find the first derivative, set it equal to 0, but you're going to plug the values into your original function versus looking at increasing and decreasing and concavity. So here's an example. Find your absolute maximum and minimum values of f of x on your closed interval. So notice I have that closed interval. Now what you have to do is you have to read these directions carefully, because it's also asking you and state where those values occur. When they ask you to state where those values occur, they're looking at the x values. So think of your x like a location. When they want you to find the absolute maximum and minimum value, that's where they want the actual y value. So there's two things they want here. They want you to find the absolute minimum and maximum value, which means they want you to state what the actual y value is. And where those occur are the x values. All right?
Put it as a point, or do you have to say
You won't put it as a point. Okay, we'll talk about, you can put it as function notation, like f of x equals something. All right, so again, first step, I'm going to have to find my critical points. So just like I've been doing, I'm going to find my critical points by finding my first derivative. So f prime of x is going to be equal to 6x squared plus 6x minus 12. So I'm going to set my derivative equal to 0, and right away I know I can factor out a 6. And I can factor x squared plus x minus 2 into x plus 2 times x minus 1. So then what are my critical values going to be? My critical values will be what? At x equals what? Negative 2 and 1. So now I call my next step my candidates. My candidates being, these are the possibilities as to where my absolute maxes and mins are going to be. Since you're dealing with a closed interval, you're not only going to include your critical points of x equals -2 and 1, but you also have to include your endpoints. So when you have that closed interval, your candidates of where the absolute max and absolute min can occur are not only at the critical points, but also at the endpoints. So any questions on what my list of candidates are going to be? So now what I always do is I always make a table. Just a table of values. My first column has the x values. My second column is my f of x. And what I'm going to do in my x column is I'm just going to list my candidates. So again, my candidates turned out to be -3, -2, 1, and 2. So now remember, what you want to do is we want to calculate the actual y values at each of these x values. So what you want to make sure you remember to do, you're not plugging these values into the first derivative. Again, you want to plug them back into the original function. So when I plug in -3, I know -3 to the third is -27. -27 times 2 is a -54. Plus, let's see, -3 squared is 9. 9 times 3 is 27. And then -3 times -12 is a +36. So -54 plus 27 is -27, and -27 plus 36 is 9. We good so far? So now I repeat the same process for the other three x values. I'll plug in a -2. -2 to the third is -8. -8 times 2 is -16. -2 squared is 4. 4 times 3 is 12. And then -12 times -2 is a +24. So -16 plus 12 is -4. -4 plus 24 is 20. Plug in my 1. I end up with 2 plus 3 minus 12. 5 minus 12 is a -7. Plug in a 2. 2 to the third is 8. 8 times 2 is 16. 4 times 3 is 12. And then -12 times 2 is a -24. So that's going to give me a 28. 28 minus 4, right? So what's the largest y value that I came up with? 20. So there's my largest. What's the smallest y value? -7. So remember, the largest is where then the absolute max is going to occur. The smallest is the absolute min. So now when you write your answer, this is what you need to be careful of. All right, the table is just a calculation purpose for you. What you need to then write is the absolute max. And there's two ways you could really write this. The absolute maximum is the value that you get when you calculate the y. So the absolute maximum value of this function is 20, and it's occurring at x equals -2. So that's the location. You may also write the absolute max as f of -2 is equal to 20. You can write that function notation as well. The absolute minimum is -7, and that's occurring at x equals 1. And the absolute minimum would be f of 1 is equal to -7. So like I said, this is kind of springboarding off what we were doing when we were finding relative mins and relative maxes. But now, again, we're taking it one step further and trying to figure out what is the actual highest point or lowest point on this particular curve if it exists. All right, any questions on when you have a closed interval, how you can calculate absolute max and min? All right, so like I mentioned, what you may also have to calculate absolute extrema on infinite intervals, meaning that you have a negative infinity to positive infinity. Again, as I mentioned before, If you have a graph where the limit is going both to positive infinity from the left and right, you may have an absolute minimum and no absolute max. Or you may have an absolute maximum with no absolute minimum. Think about your reflected x squared or reflected x to the fourth. You may have a case where you have neither an absolute maximum or an absolute minimum. You notice you have several relative mins and relative maxes, but there's no absolute max or no absolute min. All right? So really, when you have an infinite interval and they're asking you for absolute max and absolute min, you've got to remember the behavior of a lot of the functions you've studied in the past. For example, when you're dealing with polynomials, you have to remember what is the end behavior of your odd degree polynomials. What is the end behavior of those even degree polynomials? What is the end behavior of log functions? What is the end behavior of those exponentials? So for example, find the absolute maximum and minimum values of f of x and state where they occur. So what type of function is this? This is what type? It's a polynomial, correct? Do you agree with that? Is the polynomial of even degree or odd degree? Even. Leading coefficient is positive 1. So what happens when you have an even degree polynomial function where the leading coefficient is positive? What's happening with the end behavior? Both ends are doing what? Positive. They're going up. They're going up. I don't know what's really happened in the middle, but I know that they're both going up to infinity. So what is that? What can we conclude then about this graph of x to the fourth plus 4x? What's it not going to have? Exactly. So there's going to be no absolute max. Again, because I know the limit as x goes to positive and negative infinity is going to be infinity. And since this is an open interval from negative infinity to infinity, the only candidates of where an absolute minimum is going to occur is at a critical point. So I'm going to have to find my first derivative, which again I know the derivative of x to the fourth is a 4x to the third. Derivative of 4x is a 4. So the only possible candidates of where your absolute minimum for this function is going to be is at the critical point. So now I have to take this derivative and set it equal to 0. How do we solve this? Yeah, Ethan?
You could first factor out a 4.
You could factor out the 4.
Or you could just move it over to the
Move to the other side, exactly. So you could do factoring, or you could just factor in your cubes, or you could just subtract the 4. And then you can divide both sides by 4. And then what is the cube root of negative 1? Negative 1. Is it plus or minus 1 or just negative 1? Just negative 1. All right. You still want to confirm, guys, as we go through examples, always take that second to check and make sure this is indeed a minimum. You know how to do that by taking your number line and dividing it up, plug in negative 2 into the derivative. So again, just to confirm that this is indeed a minimum, because sometimes there'll be problems where you'll get more than one candidate and one may turn out to be a relative max versus a relative min. So again, if I plug in negative 2, I know that that's going to give me a negative. If I plug in 0, that'll give me a positive. So it does pass that it is indeed a minimum. So I only have one candidate. You still have to calculate the y value because it's asking you for the absolute minimum value. So you have to take negative 1, remember, and you're plugging it back into the original function. So negative 1 to the fourth is 1, plus 4 times negative 1 is a minus 4, which is a negative 3. So I have no absolute max, and my absolute minimum is going to be negative 1 at, excuse me, not negative 1, negative 3 at x equals negative 1. Or you can write f of negative 1 is equal to negative 3. Sometimes they won't ask you for both. That's why I'm emphasizing this. If they want the value, it's just the y value you better give them. If they want to know where is it occurring, you've got to give them the X value. Remember, X is your location. Yeah, Jane?
How would you find the absolute max or min if like both the endpoints are going negative infinity and like the curves are like the y value?
Then they both would be considered.
Absolute.
Yeah. You'd have two locations where the absolute maximum or minimum's occurring. You'd have two different locations. The value's the same, but again, you'd have it two different locations.
You could say it was like the absolute maximum is this at this.
X equals 5, and yeah, exactly. So if it was like 50, so the absolute maximum is 50, but it's occurring at X equals 5, and let's say X equals negative 3 or something. Okay? So you just have two locations. All right, your sketches, your favorite. Sketch the graph of a continuous function. So there's a key word, no holes, no asymptotes, continuous. With the stated properties. Now notice they're giving you a closed interval from -5 to 5, so nobody better be putting arrows on the ends of their graphs. So they're telling me I have a relative minimum at -3, a relative maximum at 2. Now, they're telling me I've got an absolute minimum at X equals 5 and an absolute maximum of X equals -5. So nowhere are they giving me any idea what the Y values are at any of these X coordinates. All I do know is that at X equals 5, this point better be the lowest point on this graph. So I'm just going to put it down here, and let's call this at -1, 2, 3, 4, 5. We'll call that -6. So I'm going to put my point, my absolute minimum, down here at -6. I do know that I have an absolute maximum at -5. So I do know at -5, this better be the highest point on my curve. So I'll see 1, 2, 3, 4, 5, 6, 7, 8. So no matter how I construct the graph, I do know that these 2 points, no other points can go above X equals -5 or go below X equals 5. Now I have a relative minimum at X equals -3. So I'm just going to put a point somewhere at -3. And a relative maximum at X equals 2. So to be a minimum, I know that it's going to have to take a turn at -3 and come back up. To be a maximum, I'm going to take a turn at 2 and go back down. Again, you may need to readjust your points if you need to. But just make sure your conditions work. I have an absolute minimum at 5, which I do. Absolute maximum at -5. I have a relative minimum at -3 and a relative maximum at 2. Okay, so any questions, guys, on the difference when we talk about relative min and maxes versus absolute maxes and mins? So really what we're going to do next class is we get into the application. We call them the optimization problems. So word problems. We did related rates when it came to derivatives. These are going to be our optimization, being able to find maxes and mins, maximizing and minimizing things. That's what we'll do on